Today, we're going to talk about hamburgers. I'm pretty good doing hamburgers. I do this for my family. I like barbecuing, and I like to do my own patties. And I buy meat at the supermarket, and then I mix it with my, a little bit of soya, a little bit of mushrooms, prepare every patty, turn on the grill, put them on the grill, start to check whether they're getting done or not. And soon I start realizing that some patties are thicker than other patties, and the grill has areas which are hotter than other areas. So I spend a really long time checking every patty to make sure it's done, and it's not done. So I keep on checking. And eventually, the patties get done. I make the hamburgers I serve to my family. They love it. I'm a hero. I'm a great chef, and everyone's happy. And then I go stronger, and I say, what could it be? Imagine what could it be to serve patties, not for 10 people or 20 people, but for 1,000 people. And the first thing you think is like, okay, I need a bigger grill. I'm gonna get this humongous grill, and then I'm gonna have people come to me, and I'm gonna serve one patty after another. And then I realized that if I have 1,000 people on a queue, and it's gonna take 1 minute to serve one people, I'm gonna need 16 hours to get them all served. So I cannot really serve one hamburger a minute. I have to serve like 60 hamburgers a minute to make that happen. And how can you serve 60 hamburgers a minute? I am Miriam Pena. I've been doing Airland since 2000-something. I don't know exactly anymore. I don't want to count anymore. I work as a staff engineer at AdRoll in San Francisco. It's a marketing advertising company. We're going to talk about them a bit later today. I'm organizer of the Airland and Elixir meetup in San Francisco. And I have a really strong back-end background. I really love to architect and build systems at scale. That's my passion. And my journey through Airland has really brought me all around the world. I was raised in Madrid, but soon I jumped into my project. My first project at scale was in Egypt for Ericsson. Then I went to Stockholm to work with Airland Solutions for an automobile company. Then I went back to Madrid for a social network, and then to Ireland, and then to San Francisco. It's been 5 countries. Looking forward to see what the next country is. The thing is that in the very beginning, I did not know how to build airline systems at scale. Like, all I was doing is to have my single node running in my computer at my office, and I didn't really have that much traffic over there. But it was great because I was actually monitoring like thousands of systems, and it scaled for me, and it really helped me. Airline helped me to develop these connections to every machine and in a really efficient and fast way, and it worked great. But then people was talking about how do you do distributed systems at scale, and I had no clue, honestly. I remember being at a conference in Stockholm, and I was like, seriously, how do you do this? I don't know. I read the documentation, I don't understand. And so now I built this talk as a talk I wish I had received back then to give me some ideas of how to do this. So let's start. Let's talk about the process model in Airland. And note, I have a strong Airland background. I have some hours of Elixir, a lot of them. I love it. But I tried to build this talk saying Elixir all the time, and it did not work out, so I'm going to say Airland. But it is really the same concurrency model. So everything that I say apply in the same way. Who are familiar with Amazon infrastructure here? Yeah, OK. So that orange thing symbolizes an EC2 machine in Amazon. With the white thing, I symbolize an Airland node, and then we have 2 processes inside there. And Elixir processes are not to be confused with operating system processes. They are so much lightweight. You can have so many more of that. You can have tens of thousands running in one node with concurrency and sending messages to each other, and it all works out magically and wonderfully. So how you take advantage of concurrency and processes by spreading the work. Let's say you have a request that comes to your system. You make the basic decoding, and then you can delegate every part of checking for something about your request into several workers. You can spawn them, even if they're not in an OTP tree. You can have one checking for the system health, because maybe there is some major outrage and you should not do anything at the moment. While another process checks the user information, we could as well spawn other processes which read from different databases, because you might have this information spread out. Then you validate the request in another one, and maybe you have just a forward one, which the only thing it does is standing there looking at the watch saying, you have 20 milliseconds to respond to this request, otherwise you're not going to make it on time. And this is the magic of Airland. And you can organize many of these processes to do some heavy work for you, in a lot of them. And then you realize that it's not enough, so you need more computation. And you need to add memory, you need to add CPU. So what do? You get a bigger machine. And it works magically. Airland, if you offer them more cores and more memory, it will be picked up by the emulator, and a lot of the processes will be spread among the new cores. But it's not enough, so you get a bigger one. And this is the biggest one. It costs $26 in Amazon, $600 a day to run this machine. And you can do so much, but you can only do so much with it. And so you have to eventually start doing horizontal scaling. And you actually heard that it's good for you, but you just don't really know how to do it, but it is. So what is this about distributed Elixir? How does this work? I'm going to put an example with two nodes running in the same machine. Node 1, node 2. When one of them starts, another operating system process called EPMD, Airland Port Map Daemon, will also launch. And that will happen on a very specific port, the 4369. And that will act as a dictionary for listing all the nodes that are available in that machine. So if you want to talk to a remote node, you have because the thing is that when you want to talk to a remote node, you have the address, but you don't know the port, because since you can have several nodes in your machine, everyone can actually be launched in a different port. And that's the way you can figure out how to connect. You understand up to here? Yeah, cool. So how do we connect them? You have two nodes here. The one on the left is node 1, the one on the right is node 2. And if you ask which is your name, there's a command for that called Airland node, and it will say, I'm node 1 at Kuro. And same thing if you ask the second one, I'm node 2 at Kuro. And there is many ways to connect them. One way could be just ping them. You can have the first one, ping the second one, and say, and if the response to ping is PON, that means that they were able to connect to each other. And from that moment, if you ask them, how many nodes are you connected to? Every single one of them will list the other. And then you can do things just in the same way as they were local. You can do an RPC call to the other node executing any command. You can ask them, what's your node name? And you will see that it's executing on the other node because it returns node 1. You can do gen server calls, having the name of the gen server you're reaching out and the node where that gen server is, asking for the state, and it will return something. You can do the old school send a message. You have the PID of the remote node. That works too. It's transparent. You can use tasks. It's really just the same. And this works for many processes. They don't share their ETS. They share the global namespace. And basically, every node will be connected to each other. And now you know all you need to know. This is it. Isn't this wonderful? Don't you love it? I love it. It's great. Looks so easy. You're free to go. A real world is not like this. Networks go down, internet goes off, you have the network splits, your node will crash. You may have a buggy mobile client that keeps on reconnecting, and since it is a mobile client, you cannot really get rid of it, so it's very annoying. And maybe Amazon will decide to restart your machine because they need to do some maintenance, and maybe you forgot to check the email in which they informed you about it. Maybe there is something going on in one region, and you receive, and since that region is not operable, you will receive all the traffic from your region in your other region. So basically, you will have twice as much traffic in 1 minute, which happens all the time. The thing is that you cannot really expect to be able to reach a remote process, and you have to be prepared for chaos. Basically, everything that can go wrong will go wrong. So what's going on here? Some of you might already realize the problem here. All the nodes are connecting to each other. This means that as the number of nodes grow, the number of connections you will require to serve all this traffic is going to grow in a very, very aggressive way. Like you're going to need 5,000 connections for 100 nodes, which are not really that many. Then the latency on our RPC call will increase as the cluster size grows. And some say, like, how much can it grow? And it really is up to what your application does. Like, if you don't have a lot of remote things going on, maybe you can have 100 nodes connected and they work fine. But if you have that, maybe 10 is already too much for you. And definitely 1,000 is something that very complicated to do, and over 100, you really need to know what your system is doing on the back, and tune your network interfaces and a lot of that. And then also, you should not really be able to reach a remote node. Network splits happen. When that happens, it's really detected almost immediately for the most part, because TCP's magic has this magic doing that. But sometimes it takes up to 60 seconds because you have to actually go through the heartbeats. It's 4 heartbeats every 15 seconds. If you miss the 4, then you get this notification. And when the split happens, if you are linking to a remote process or you are monitoring a remote process, you will receive a node down as well, one of those messages saying that your process is unavailable, and you will receive thousands of them at the same time, and that will really increase your message queues. So it's a bit tricky to do. And also think, what happened if you were in the middle of a transaction between 2 nodes? Should you repeat your transaction? Can it happen? Does it have to happen at least once, or at most once, or does it have to happen strictly one time? And those are considerations. Another really funny thing about connecting nodes is the concept of security, the false concept of security on a cookie. And a cookie is a shared secret that is it was designed only for topology. You cannot, it's not really a way to secure connections. You have to do something else. And there is SSL distribution, which I have never used, but I heard it's there, so maybe that's an option. Or another option could be to cipher your protocol, or maybe do something on a lower level. But you have to keep that in mind. You can just connect nodes and be OK with that. Just for a funny thing, how this works, if you have one node and another node which doesn't have the same cookie connected to you, trying to connect you, it will complain. It will say this funny message that is disallowed. And another very worrisome thing is that if you have managed to find a cookie and you have managed to connect to that node, you have access to every node that is on your network, and you can do really funny things like this, like remove a ref all your file system from a remote node from anywhere else, which is a bit interesting. RPC calls do not scale. because when you do RPC call to a remote node, all the RPC calls are executed in one single process. It's called Rex, I think. Yeah, the Rex process. That means that you have to use something else, maybe GenRPC, or maybe you can do your own thing, some processes with some names, and you reach out to them individually. But you have to be mindful of this. And with this, I'm going to start. We're going to have two examples today. The first one is 20. It was a chat server I worked for a long time ago. We were running in Spain. We have over 1 million users running at the same time. It was a really big cluster. We were bigger than Facebook for some time, and then they ate us, but we were there. And we were hosting our machines in our own data center, one of those buildings with control access, a lot of gates in between you and the data centers. So distribution Airland wasn't a concern for us in terms of security, and that's why we opted to use it in a very popular tool called Yaberd, which is also now released as Mongoose IM. And having several of these nodes connected to each other with Nisia, it was still really easy to do, and it worked really great, and it scaled really well. Basically, when a user will reach the servers, will randomly, because of the magic of the load balancers, be assigned to any of the nodes. And that node will put that user information in the database. And Nisia is a distributed real-time database, which can store the data in disk or in RAM. And that means that when that information is stored there, it will automatically be replicated on a remote node. So when later the user wants to talk with each other, it will just look on the local database for what's the PID of the other, and it will just send it the message through message passing. The thing is that when you want to do this for 1 million connections, for 1 million users, we needed to go a little bit beyond that, and because we couldn't have the whole cluster connected through Airland for the reasons I mentioned before. So we did federations. Basically, we were using this concept that when you talk with someone, most of your communications with that on your daily are within your local city or at most within your local state. And for us, it meant that if we could put all these users from the same state on the same domain, 90% of our traffic will stay within our domain, will not reach the other domain. And this was very convenient because you can have 90% of the traffic connected to each other through Airland distribution and 10% reaching a remote domain through XMPP. And bear in mind that these were machines, all of these domains were served for machines in the same data center. They were not really a different region. It got to a point in which we grew too much and Yaberd wasn't enough for us. So what we did was to do something which is in concept really similar to Yaberd, which is to have some sort of distributed ETS tables. And that worked really well. It was a bit hacky, to be honest. We did a lot of really nasty things to make it scale. But another solution, which probably I would have done now, is to just use some external database, maybe a memcache thing, and have everyone connect to there via TCP. And second example, AdRoll. So imagine yourself, like what we do at AdRoll. What do we do at AdRoll? Imagine yourself browsing the internet, and there's like this backpack that you love, and you're browsing over it. And eventually, you go to maybe the New York Times, and you see an ad of that backpack, exactly that backpack. And that's what we do. We serve ads of things that you like, and we use information that we gather from your browser to decide what's the best ad to serve you. And AdRoll has really interesting challenges because of the numbers we're handling. We're handling 1.3 million of these requests per second in our Airland clusters. Those requests match to up to 2 billion cookies. we have 37,000 clients worldwide, over 1,000 Airland nodes in our cluster in 5 regions, US West, US East, Ireland, Tokyo, and Singapore. And the real challenge is that every request we receive, every one of those 1.3 million have to be responded in less than 100 milliseconds. So there's not a lot of room to query Postgres and do things like that. And it's really funny because since we don't have room to query Postgres, what we do is to flush Postgres to a file, and we just move that file to an ETS, and we have everything in an ETS instead of querying it. That's another story. But AdRoll was not always like this. AdRoll many years ago was really small, and they were designing these very early things. And one of the things one of the biggest problems they have is that they needed to protect themselves from overspend. And think about you have 1,000 nodes, and you have one of your clients, and they give you like $100 to spend a day on ads. And you have all those 1,000 nodes spending money on ads. And how do you know how much every of these nodes have spent, and how do you protect yourself from overspending more than $100? Because if you do, you have to pay that price, and that's not really great if you want to make a business. So what we do is we use Airland distribution for this. We have, let's say we have 3 nodes, and these 3 nodes will be connected to a remote, go back, yes. To a remote node called body. Could be like a master thing. And what happened is every node for every campaign our clients had was sending a message every minute saying how much they have spent on that campaign. And if you think about it, it did work for some time, but then it didn't, because that's 37,000 messages per node per minute. That's a lot for RPC call, because we were using RPC call, because we didn't know what else to do at that moment. And that remote node, what we'll do is to gather all this information and add them up and keep track of how much we were spending, and if there was an overspending, we'll notify the nodes so they would stop spending. So a solution was to, instead of sending the message to this body remote node through Airland distribution, was to send it through a bucket in S3. You all know, is anyone, bucket, you know what S3 is, right? Yeah. So every node will send a file there, and then we will have another independent process, initially written in a different language, which was called SpendCop, that will read all those files and will do the aggregations. We will check what the state is, and they will generate another file with a report of the state, put it back to S3, so every node could read it, and they could react to it when we were overspending and stop bidding aggressively when that happens. So this is a sample of how you evolve your system. You start with Airland distribution, it works well for a few years, and then it doesn't, and then you do something else. Another way to scale the system, which is talked a lot recently, is just to remove functionality from it and put it on a different system and have your main nodes connecting to there for some piece of work. And we did this for pricing. Pricing is deciding how much we're willing to spend to show an ad to a specific person for a particular campaign. And this computation is designed by our data science team. The data science team in AdRoll, they have an artificial intelligence system which is fed by all the past information about how we bid, and when we win, and when the actually clicks happen. And the thing is that they, of course, they are doing these models all the time, and they wanted to replace these models all the time. So they needed a way to do it. And the best thing we thought at that moment was to have them doing code replacement. Basically, they will program a new version of their model, and we will do hot loads in our nodes, and we'll launch the new code. And they could do it quite frequently, and this was really great for them because they give them a lot of flexibility. It wasn't that great for us because sometimes they break our systems when they ship a buggy piece of code. So eventually, we suggested they move away, and they created another program on the same machine for pricing, and eventually they just use their own clusters for it. And this let us really scale independently because the demands of every system were very different. The nodes are bounded on CPU. That's our main problem, where their pricing was bounded in memory. So they needed so many fewer nodes to do the same work. And so maybe they have a cluster of 3 or 4 or 5 when we have a cluster of 500 to serve the same amount of queries. And it was really easy to debug. They can do independent deploys, and it was very convenient. We're very happy. So takeaways of all this thing I'm just telling you. The distribution model could be really great for a handful of nodes, for a few nodes. And I really encourage you to try and use it and make it work for you. But you have to be very mindful of the security layer. You have to try to serve as less state as you can and avoid remote calls to a single process by doing different libraries that prepare you for that. Avoid doing remote links, avoid doing monitors, and be prepared for failure. Be prepared to react to that. Like, do you need that piece of code to execute at least once, or at most once, or exactly once? For big clusters, maybe just don't do it, because it will not work probably right. There's a lot of theory out there, and you can make it work, but it's probably not worth the hassle. Probably just do normal, a different protocol. And there's really no magic formula for scaling systems. If only one, don't over-engineer in the beginning. Start simple with a small thing that works end to end, and then iterate over it and learn how to make it grow. Find the next bottleneck, adapt to it, and scale. And just like hamburgers. You remember the hamburgers? We can apply all these learnings to make hamburgers at scale. We can, like, how do you cook hamburgers for 1,000 people? You pre-cook the patties, because there's no way you can have a big grill for 1,000 people and have them all at once. And then you scale vertically by having bigger stations with the patties and the tomatoes and the onions and the burger and the bread, and have everyone picking one of each. And then you realize that one station is not enough, so you have several of those stations, one next to each other. And then you realize that you have to actually separate them a lot, because otherwise people will be, it gets just too crowded and everyone will be connected to each other. And it's probably not enough, because it happens that most of the people are really picky about their patty they pick up, because some want them well done and some want them rare. So they're gonna really stand there staring at them, thinking maybe I like this one or not, and your queue is gonna be very, very slow. And then tomatoes will fall to the ground, and it will be dangerous for them, and it's just not working. So eventually, the best thing you can do to serve 1,000 people hamburgers at scale is to pre-prepare the hamburgers. Have each hamburger on a plate, and have the plates on the stations, and everyone just pick a plate and move on. And maybe this reminds you of something. Yeah. Any massive scale production system has to deal with these kind of problems. Thank you.